Now let me just keep playing with my microphone for a minute. Get it so I can talk. All right, so do we have sound? Yes, we do have sound. Okay, so this week the lab is hydrated salts and gravimetric analysis. Okay, so first off, what is a hydrated salt? A salt, remember, a salt is just any ionic compound. So sodium chloride is a salt. Magnesium hydroxide is also a salt. Just any ionic compound is a salt. Hydrated means we're looking at a solid solution. So ordinarily when we think about solutions, we're typically thinking about water with stuff dissolved in them. A solid solution is just some solid where you have a solvent and a solute. That's not particularly unusual. Steel is a solid solution of iron and carbon and other things. In the case of a hydrated salt, it is a salt with water dissolved in it. That's perfectly fine. The salt just incorporates water into the crystal structure. And when they do so in a very regular fashion. And the result is, let me move the video camera. The result is, examples like this, where you have 6 water molecules incorporated for every unit of iron 3 chloride, or 5 water molecules for every unit of copper 2 sulfate, 7 water molecules for every unit of magnesium sulfate. Okay. So hydrated salts are incredibly common. Those things that you get in your shoes or in beef jerky or a whole lot of other things that say silica gel, do not eat. Those are drying packets. They contain dehydrated salts, and over time they will absorb water from the air around them. It's meant to keep the shoes and the beef jerky and so on dry until they arrive so that they don't get mildewed inside. So first, I would like to talk about naming hydrated salts. It's actually very straightforward, very simple. All you have to do is just name the salt as usual, and then it gets a little weird. So, but not very. So let's look at the first example from the page there. We have FeCl3.6H2O. Okay. So we name our salt. We have iron. It can take multiple charges. And then we have chloride. Okay. Chlorine takes a -1 charge. There are 3 of them for every one of the iron, so the iron has to have a +3 charge to balance it. So it's iron 3 chloride. Now for this, it is a hydrated salt, so we just say it is hydrate. And then whatever the number in front of it is, we go ahead and use the same Greek prefix that we use for covalent compounds. So this is the time that you would see a Greek prefix in an ionic compound, is when you're dealing with a hydrated salt. So this salt is iron 3 chloride hexahydrate. The next example that we have there is this guy here, CuSO4 dot. The dot is important because we want to indicate that the salt is part of the solid. It's part of the mixture, but it's not chemically bound to the copper sulfate. Okay? In fact, this is not just copper sulfate. It is copper 2 sulfate, because copper, again, can take multiple charges. And then we're looking at pentahydrate. And the final example, MgSO4 dot 7H2O, magnesium sulfate. Magnesium can only ever take a 2+ charge, so we don't need the Roman numerals. And then heptahydrate. All right. So lots of salts can form hydrates, and naming them is relatively straightforward. This lab is going to be about finding the formula of a salt that has been hydrated, and you're trying to figure out what the hydrate is. Unless I'm totally brain farting. Let me double checking live. All right. Okay, so in any event, if you take a salt, a hydrated salt, and you heat it up, you will drive off the water. So say you have our copper sulfate, copper 2 sulfate, pentahydrate. You heat it up, you'll drive it off, and you'll end up with copper 2 sulfate in the solid form plus H2O, boiling off as a gas, more or less. This means that the solid that gets left behind will be lighter than the solid you started with, because the solid you started with included water. The solid that gets left behind no longer has that water. Okay. So that is the really straightforward part. The heating, to be careful, they do it multiple times so that you can get, to be sure that you've driven off all the water. So you heat, you weigh it, you heat it, you weigh it, you heat it, you weigh it. Once the weight stops changing multiple times in a row, then you know you've driven off all the water, and you can be confident that all you have left is the salt, the dehydrated or anhydrous salt. So that's the word they use there. Hydrate, anhydrous. So hydro, of course, meaning water, so anhydrous meaning without water. So to compare this, let's look at what am I talking about? Molar mass. Okay, so let me open up my periodic table. Oh, you can't see all of that. I'll close this real quick. So here we have copper is 63.546. Sulfur is 32.06. I believe it's 066 actually. Let's see. Oxygen is 15.999. And then hydrogen is 1.008. Okay. So in the copper sulfate pentahydrate, we have one. Oops, let me go ahead and bring the camera back up so that you can see what I'm doing. We have one copper atom in every unit of the hydrated salt. We have one sulfur atom. Now, you have to be careful about the waters, because there are 5 water molecules, so there's going to be 10 hydrogens and 5 oxygens from the water. There's also 4 oxygens from the sulfate. So 5 oxygens plus 4 oxygens means we have 9 total oxygens and 10 hydrogens. So let me bring up my calculator so that I can do this math. So 63.546 plus 32.066 plus, parentheses to be safe, 15.999 times 9, close parentheses, plus, open parentheses, 1.008 times 10, close parentheses, enter. So that means that you add all these up, and the hydrate has a molar mass of 249.683. And the unhydrated salt, the anhydrous salt, would just be these two plus 4 oxygen. $63.546 plus 32.066 plus 15.999. 1, 2, 3, 4. 159.608. Okay. So our hydrated salt, 249.683. Our dehydrated salt, 159.608. And just to be thorough, the 5 waters is going to be 10.08 plus, let's say that's 5 oxygens, 15.999, 1, 2, 3, 4, 5. 90.075. Does that add up? 3 8, 6, 9, 4, 2. Yes, okay, good. No mistakes in my math anymore. All right. So one way of representing the fraction is to talk about mass percent. Because a mass percent is easy to calculate because we can measure the masses very straightforwardly. We have our total mass at the start. We have our total mass of the salt left over at the end. So one way would be to have the anhydrous over the hydrated would be 159.608 divided by 249.683. 159.608 divided by 249.683 is 63.924%. But because reasons, we don't typically talk about it in that terms. We instead would do the H2O over the hydrated salt. And it would be, 36.076% water. Just because that's the way we'd do that. But that's all a mass percent is just a mass divided by mass. In this case, we're looking at 1 mole of the substance. But if we started with 5 grams of this hydrated salt, we would end up with something like 3.2 grams of the anhydrous salt. And then we would just go back and we would find out how much water we lost. So let's go ahead and do that math. Okay, so let's keep on working with this copper sulfate. So CuSO4.5H2O goes to CuSO4 plus 5H2O. Say we started with 5 grams of this copper sulfate pentahydrate. Let's go ahead and find the mass of copper sulfate we would have left. Okay. I'm going to go ahead and do the molar mass math because I think, well, you're going to need it for Chapter 6, so we might as well, get some review, get some practice on that. So the molar mass of this copper sulfate pentahydrate was 249.683 grams per mole. So 5 grams divided by that big number there means how many moles? I know I hit enter. Okay. Is 0.02002 moles of the copper sulfate pentahydrate. So let's go ahead and make that clear. Now, this is fortunately a really simple chemical equation. They typically are for a hydrated salt. And the result is that there's always going to be a 1-to-1 mole correlation between the hydrated salt and the anhydrated salt. Okay. Whereas there's a 1-to-5 ratio between the hydrated salt and the water, because 1 mole of the hydrated salt will release 5 moles of water. Okay. So that means that, times 1 mole of the copper sulfate is going to be produced for every 1 mole of the copper sulfate pentahydrate that we started with. So 0.02002 moles of copper sulfate will be produced. Okay, there's nothing too confusing about that. But then we just have to convert back to mass. So the molar mass of our copper sulfate, 159.608 grams per mole, means that after we've heated it up and driven off all the water, we will be left with Oh, I got that really close. 3.196 grams of copper sulfate. Yeah, I predicted about 3.2. Okay, I'm awesome. Let me just say that. I am awesome. So we start with 5 grams of this copper sulfate. We heat it up over and over again. We drive off all the water. We should be left with 3.196 grams of the copper sulfate. Now, mistakes can happen. If you don't heat it up sufficiently, you might not drive off all the water. You might have too much mass. If you heat it up incautiously, the water can boil out of the salt, and it can crack and pop, and you can lose some of the solid. You'll end up with too little mass. But still, you should end up with around there, depending on how careful you are, how clean your crucible is, things like that. All right. Okay, so in order to work this lab, you are going to do pretty much this in reverse. Okay, you'll have, say, something like copper 2 nitrate dot X H2O. Okay. You won't know what the formula is. I believe that's what you're trying to find. Okay, so what you'll do is, say you start with 10 grams of your salt, you heat it up, you drive off some amount of water. Let me figure that out real quick. Oh, I should have. No, well, you're going to drive off some. Oops, well, I didn't mean to do that. There we go. You drive off some amount of water. Say you're left with. Let me do some math in my head real quick. Oh, I can't do that math in my head real quick. All right. All right, I'm going to have to use the calculator here. Just 65. 63.546. I'm sorry about this. Oops. There we go. So it's going to be 277.637. All right. Okay, I think I have all the info I need. Well, not quite. Let's see. Okay. So, again, sorry about that. So you start with 10 grams of this copper nitrate, this hydrated copper nitrate. We wouldn't actually use copper nitrate. It's terrible for something like this. It is so attracted to water that eventually it absorbs so much water into itself that it actually goes the other way. Instead of being water dissolved in the salt starts dissolving in the water. You end up with a gooey mess. It's awful. All right, so you start with 10 grams of your salt. You heat it up, you heat it up, you heat it up. You drive off all the water, and you're going to be left with 6.755 grams of your salt. Okay. Which means how much water? Okay. Well, if you have 10 grams, you heat it up, and you drive off all the water, you're left with 6.755 grams. Then it's just 10 minus 6.755 leaves you with 3.245 grams of your water. This will allow you to go back and find out what the formula for your salt is, because 3.245 grams, actually, let me see if I'm not screwing this up. Well, let's just keep on going. You convert this into moles, so you divide by the molar mass of water, 18.02 grams per mole, and that's going to leave you with the 0.18009 moles of water. Okay. So you heat it up 10 grams of your copper nitrate pentahydrate, and you produced the 0.18009 moles of water. I am thinking my way sideways around this, aren't I, Sasha? You can't see him, but my cat is here being adorable. All right. Oh, I can't look at that. But I can look at the worksheet. Make sure I'm showing you what you need to know. Sorry, I should have done all this before, but what can I say? I was sleepy. I slept all day. Okay. Oh, duh. That's why I'm screwing up. That's what I forgot. Okay, so you have your hydrated salt, you have your dehydrated salt. Good. That was all the spark I needed. Okay. So we know the molar mass of our anhydrous salt because we know what the formula is. So that's 63.546 plus 14.01 times 2, because there's 2 nitrogens, remember. That's why it's important to have the 2 there. And then plus 15.999 times 6. 3 times 2 is 6. This gives us the molar mass of our salt is 187.562 grams per mole. Means we're looking at how many moles of our salt. 6.755, unless I've screwed up, it should be the 0.036. Divided by 187.562, yes, good, is 0.036014 moles of copper 2 nitrate. Okay. So now we can get the ratio between the water and the salt. Good. I knew I was heading in the right direction with this. Okay, I was just coming at it sideways. In other words, we're trying to find X. So if we divide the moles of our water by the moles of our dehydrated salt, the answer will be very close to, not exactly, but very close to a whole number, and that's X. Okay, so 0.18009 divided by 0.036014, because we're finding the relationship between the moles of water and the moles of the salt. Okay, and that's all that this represents. It's a 1 to X ratio for almost every salt out there. So you divide these through, you get the ratio, you get X divided by 1. Okay, so 0.18009 divided by 0.036014 gives us a number that's very close to 5. Okay. So that's just rounding errors from all the math I was doing. So the X equals 5, meaning that the formula for our salt is copper 2 nitrate pentahydrate. Okay. So that is how you're going to have to do this. Okay. You heat it up, you heat it up, you heat it up, you drive off all the water. Okay. So you're going to have the mass you started with, the mass you end with. So this right here is your hydrated salt. You can't know how many moles there are because you don't know X, so you can't find the molar mass. But then down here at the bottom, this mass, the mass of the salt that's left over, you subtract out the crucible. Don't forget to subtract the crucible. This is your anhydrous salt, your dried salt. And that you will be able to know the formula. That's just this first part right here. But from that, you can get the mass of the water because the amount of the mass that was driven off was all water. So the 10 minus the 6.755, that's what gives us the mass of water. Okay. But remember, there's a reason we work in moles, and it's because the mass ratios are never ever going to be the correct ratios. You always have to work in moles. So you find the molar mass of the salt, you find the molar mass of water. Mass of the salt divided by the molar mass of the salt gives you moles of salt. Mass of water divided by molar mass of water gets you moles of water. And then you find the ratio of those two moles, and that will get you that number right there. So mass 1 minus mass 2 gives you mass 3. Mass 2 is the mass of the salt. Mass 3 is the mass of the water. Convert both of those into moles. Moles of water divided by moles of salt gives you your ratio. Okay. So that is how this works. We can also report it in terms of mass percentages. Once you've done this sort of work, you know what sort of numbers you're working with, then mass percentages can be a shortcut. Because in this case, you know that the water is about 32.45% of the salt by mass. So you have an unknown copper salt, you drive off the water, it's about 32% lighter. You know, then that's an okay indication. Not perfect, but okay indication that you're looking at copper 2 nitrate, that sort of thing. There are other ways we can work with mass percentages. Let's see, there have been other things where we deal with other salts, where you get other reactions in addition to driving off the water. But for this one, I think they're just sticking with this right here. From your hydrated salt to your dehydrated salt, then you have your two masses, salt and water, separate. Convert them both to moles, find the ratio. All right, so that is what you're doing for Lab 7. I should have done some of that prep work beforehand, but hey, doing stuff on the fly is what gives spice to ye old life. All right, and with that, I am done with this lab. I wish you luck of it, and I'll see you either next week or the week after. See you around.